So what I have here is, again, just your typical distillation column setup, but something that I might want to point your attention to here as I try and get my pad to work is we have introduced this thing called a splitter. And this splitter is essentially what takes in our total condenser output, the liquid output, and it splits it into the liquid flow to the rest of the distillation column and a distillate flowing out of it to be used as product. So our goal here is to do something called a degree of freedom analysis. And so what we're going to do is we're going to take each stage listed here in our distillation column setup, and we are going to determine, using an analysis of the variables and the equations involved, the minimum amount of specification that we need to provide in order to run this distillation column effectively. So we will do this stage-wise. We're going to do this for a condenser, a total condenser. We're going to do it for our splitter. We'll do it for our rectifying section. We're going to do it for our feed stage, our stripping section, and our reboiler. So first thing is maybe what more likely you would do one of these analysis on is our equilibrium stages. So any one of the stages in our rectifying section or our stripping section. So you're going to have a vapor, or I guess this is our liquid flowing down through the stage, and here is our vapor flowing up through the stage. So this is what I'll call our equilibrium stage. So first things first is, what are our variables? So the first thing that I'm going to look at is, what are our stage-wise variables? So you're going to have a temperature of your stage. You'll also have a pressure of your stage, as is set by, maybe valves, constricting valves, maybe opening up valves. And then you're also going to have some sort of temperature control, maybe a water jacket or something of that nature to help control these two aspects. And then you're also going to have your stream variables. So these are the variables per stream. So you're going to have a component stream. So this is defining what is flowing up through this the system. So you're going to have a C number of components. So I'll say like component. So this is temp, pressure, and so this attributes for one variable. This component attributes for C variables. And then you're also going to have a temperature and pressure of the streams. So you're going to have two more variables to worry about there. So something else that you have to consider when you're looking at the stage-wise analysis for your variables is your heat flow in and out of your stage. So depending on if your stage is insulated or if it's able to freely interact with the surroundings, you will have some sort of heat flow present within your stage. So that is also something that you can put in your stage-wise variable. So this heat flow, I'll just say heat. So that will also add another variable. So these stream-wise components, so you see that there are 4 streams. So there's an entering liquid stream, an exiting liquid stream, you have an entering vapor stream, and an exiting vapor stream. So you're going to have a total of 4 times the C plus these 2 temperature and pressure considerations. So now we ask, what about the equations? So first off, you will say, well, we're going to have our mass balance, and you're going to have a mass balance for each of your component streams, or rather each of your components. You're going to have vapor-liquid equilibrium, again, for each of your components. You're going to have a defining energy balance for the entirety of the stage, and what you will have is something called a temperature-pressure equality. And you're going to have 2 of these. And why would that be the case? Well, so we realize that we're going to define a temperature and pressure of the stage itself. So when we look at these exiting stages, these temperatures will be equal to the temperature of our stage. So that is one equation for this exiting stream, one equation for this exiting stream. So you'll end up with two equations for your temperature and pressure equality. Now, the last part of this analysis for just an equilibrium stage is you're going to total up your number of variables. So you're going to have 4 times C plus 2 plus 3 for the stage consideration. And you're going to subtract your number of equations. So that will be 2C plus 3. So this will simplify to 8C plus 8 plus 8, or 4C plus 8, not 8C plus 8. Do my algebra right. 4C plus 8 plus 3 minus 2C minus 3. We have a 3 and 3 here that are going to cancel, so this remains 8. And then we have a 4C minus a 2C. So this will end up being 2C plus 8. So this is your degrees of freedom. So degrees of freedom, making weird shapes here, for an equilibrium stage. So I want to make a correction here. So we talked about having this temperature pressure equality. That's basically essentially saying that whatever is exiting our stream must have the same properties of the stage itself. So we have two considerations for the temperature, and we actually will also have two considerations for our pressure as well. So what you could say is that we have temperature and pressure, so these are two separate equations, and these are going to be for two streams. So these are kind of our stream dependent equations. If we do that, this becomes 2C plus 5 over here. So let's fix that. So this becomes 2C plus 5. So this becomes minus 5. 8 plus 3 is 11, minus 5 is 6. So this ends up being 2C plus 6 degrees of freedom instead of 2C plus 8 degrees of freedom. So now let's move on to our feed stage. Now our feed stage looks very similar to our equilibrium stage, except for the fact that we now have the inlet where we are feeding into our distillation column. So a pretty, I guess, a convenient way to kind of simplify this is to say that, well, a feed stage is essentially an equilibrium stage plus another stream, so one stream. So our equilibrium stage, if you remember, had a degree of freedom analysis of 2C plus 6. Now when we add a stream, we are essentially adding that component variable. So how many components are we feeding into our distillation column? Plus 2 for our temperature and pressure considerations per stream. And now when we do this, we get an overall degree of freedom for the feed stage, which is 3C plus 8. And if you were actually to go through and calculate, or rather count all the variables and then subtract the number of equations that apply to our feed stage, you would come down to this 3C plus 8 term. So this is just a quicker way to get to the same answer. So now we come to the reboiler. And similar to how we did the feed stage, I'm not going to go through the variables. I'm just going to make a relationship back to an equilibrium stage. So now what is different from the equilibrium stage versus the reboiler stage? Well, the fact is that we don't have a vapor stream that exits our system. So when we do that, we see that we have two exiting streams still, so our temperature and pressure equality still applies. However, we can go ahead and say that this is essentially, so 2C plus 6 is our equilibrium stage, and then we are subtracting C plus 2 for the absence of an entering vapor stage. And when we do that, our degrees of freedom for a reboiler is C plus 4. So now moving on to our condenser. What we notice is that we're not putting this the distillate product leaving our condenser because we put that into a separate unit operation called the splitter, and that controls our reflux ratio. So we still go through. I'm going to do the full setup for this because there are a couple changes. So for our stage, we're going to have a heat flow, we're going to have a temperature, and we're going to have a pressure. So all of these are single stage contributions. And then we also will still have our C term for our components, and then our temperature and pressure. So this is 2. And now this is for 2 streams. So you have an entering stream and an exiting stream. We have 2 streams. For our equations, for the most part, it remains the same. We still have our mass balance, and that's going to constitute C number of equations. And we will have an energy balance, which is 1 equation, and we're still going to have a TP equality, and that's two variables for only 1 exiting stream. So this is 1 time only. What you will notice is missing here is our vapor liquid equilibrium, and that's because our system here is not at vapor liquid equilibrium. We have a condenser here that is forcing all of our entering vapor to become a liquid. So there is no equilibrium in our total condenser. So that's why we are missing that vapor liquid equilibrium contribution. So let's total up. We have 2 times C plus 2 plus 3 for our variables, minus we will have C plus 1 plus 2, so C plus 3, right? So we have 2C plus 4 plus 3 minus C minus 3. So we end up getting C plus 4 degrees of freedom for our condenser. So now let's move on to the splitter. So this is our condensate product leaving the condenser, and then we have 2 streams. We have a distillate stream exiting, and we have a liquid stream exiting to recircle through the distillation column. So we can start off by listing our variables. We'll start off with the usual suspects. We have our heat flow, we have our pressure, and we have our temperature. And then we also have to add what is our ratio of distillate to liquid. So that's the reflux ratio, actually. So that adds on another variable. And then you also have your components, and you also have your temperature and pressure of the streams. And since you have 3 streams, you will repeat this process 3 times. For the equations, again, usual suspects are your mass balance for your C number of components. You have your energy balance for the system. And then you have your temperature, pressure, equality. You have 2 attributes for 2 streams. So you'll have a total of 4 there, but we'll do that later. And then also what you're going to have is your component times your ratio. And this will give you the ratio. Basically, a mole balance is whatever is your total number of moles of one component entering. Your exiting streams must have the same number of moles in total. So you're going to get C number of this equation. All right. So now if we tally it all up, so we have a 3 times C plus 2 plus 4 on our variable side minus 2C, and then 1 plus 4 is 5. So we now have 3C plus 6 plus 4 minus 2C minus 5, and this will give us a total of C plus 5 degrees of freedom for the splitter. Now the last thing to cover is, what if we looked at our distillation column as a summation of sections? So this is, this could be either our rectifying section or our stripping section. So the first thing that I see is that we're going to have an n number of stages. So let's start there. So we have n number of stages. This in itself is one contribution in our degree of freedom. Now, remember that each of these stages is an equilibrium stage. We define the condenser, feed, and reboiler as different stages apart from our section. So we're going to have n times the degrees of freedom for our equilibrium stage is 2c plus 6. So this is the number of degrees of freedom, or rather, this is just the degrees of freedom for each one of the stages in our section. But you will also realize that we have double counted streams. How many? Well, we're going to have, I'll write it this way. So 2, this is double counted. So 2 times n minus 1, because there are n stages and minus 1 for each of the double counted stages. And each of those stages has a number of c plus 2 stream related attributes. So what do we do now? Well, we can go ahead and subtract these two values from each other. So we're going to have 2nc plus 6n minus, so let's say this is 2n, so 2 times nc minus c, and then we also have a positive 2n plus 2n, and then, did I do that right? NC, right this way, let's do it this way. So NC 2n plus 2n minus c minus 2. So 2nc minus 2nc, so these two terms will cancel out. 6n minus 2n gives us 4n. And then we also have plus c plus 2c, or minus 2c, no, plus 2c. Gosh, my algebra. Plus 4. Did I do that math right? 6n minus 4n. So 2n plus 2c plus 4. And then what we can't forget about is a plus 1 for the actual number of stages that we have. That's also a degree of freedom. So per section, we have 2n plus 2c plus 5 degrees of freedom. So these are all of the degrees of freedom that we've calculated, and I put them in order of our distillation column. And now, in order to find the overall degrees of freedom in our distillation column, what we can do is we can go ahead and add up all of these together. So throughout all of these, so we have 1C, 2C, that will be 4C, 7C, 9C, so 10C here, plus our rectifying and our stripping stages, number of stages rather. So we have 4 plus 5 is 9, plus 5 is 14, plus 8 is 22, plus 5 is 27, and plus 4 is 31. Right? 4 plus 5, 9. 14, 22, 27, 31. So here is the total number. Well, actually not quite, because if we look at our distillation column, you see that we actually have double counted streams within the column itself. How many? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So everything that isn't the feed, distillate, or the bottoms. So we actually have 9 double counted streams. So I'll say double counted streams. And for that, we'll subtract 9 times C plus 2. And so if you do that, so minus 9C, there should be a C here, minus 9C gives us C plus 2NR plus 2NS minus 18, so 31 minus 18, 11 minus 8 is 3, and then 2 minus, so 13 here, plus 13. So now here we have, this is the total number of, or rather not even number of, just total degrees of freedom in a distillation column setup. And now what we can go ahead and do is go through and specify what each of these degrees of freedom can be. So the first thing that we can say, so I'll use a different color here. So for one, what if we specify that for each stage in our rectifying, so in N, R, and NS, so each stage in the rectifying and the stripping section, say that we're going to specify our Q, our heat flow, and generally we'll say something like it's adiabatic. And we specify pressure, and we'll say that by rather saying, instead of specifying what that pressure is, we'll say that the pressure drop is negligible or that excess is flared off. So we also specify a pressure. This gets rid of our 2 rectifying and our 2 stripping. And what's left is going to be C plus 13. Next thing that I can specify is that our feed temperature and our feed pressure are specified. So specified. And this will account for C plus 2. So now what is left after this is just 11. Now, like we did for each of the stages in our rectifying and stripping sections, we can also specify the feed stage heat flow and the feed stage. We can say that the feed stage pressure drop is also negligible. So these are also specified. So this is the feed pressure and the temperature for the stream, and this is the feed heat flow and the feed pressure of the feed stage itself. And after having done that, you are left with 9. So 11 minus 2, 9. Now, also, what we can do is we can say that for each stage, so for each stage, oh my gosh, the T and P are specified. Right? And this accounts for another 2 degrees of freedom. So now we are down to 7. Sorry, I want to make a correction here. This is not the the temperature and pressure for each stage, but rather this is saying that what if we specify number of stages in each section? So this is what accounts for another 2 degrees of freedom. Now, at this point, we look towards our condenser, our feed stage, and our reboiler. And for each of the 3 of those stages, or sorry, no. So this is for the condenser, splitter, and the reboiler. And the P is determined. This takes care of another 3 degrees of freedom. So this takes us down to 4. And then we could go off and also say something like we have an adiabatic reboiler. So reboiler running adiabatically. So now we are down to 3 degrees of freedom. Again, I need to make a correction. This isn't for the reboiler. I meant to say the splitter. This is for the splitter. This is running adiabatically. Now, our last couple assumptions. So we will say that we also specify the distillate and the reflux ratio. These are specified values, which takes care of another 2, which brings us down to one last specifiable variable, and that is going to be something like the condenser product is at saturated temperature. And this takes care of all the degrees of freedom. And this list of assumptions that I just went through are the general assumptions and specifications made in distillation column design out there in the real world. So we have successfully derived each of the degrees of freedom for each stage within a distillation column, and have also specified a set of general specifications for a distillation column.